Okay, so good afternoon, everybody. So thank you, Shakuntala. And let me start by thanking the organizers, Tridib, Gautam, and Jacopo, for the invitation. And it's a pleasure to be here, back to ICTS as usual. So I have to say right in the outset that my talk will not have any hydrodynamics, okay? But it will have some noise and fluctuations, and maybe some fake quantum mechanics, as we'll see. So the outline of my talk is the following. So I will, this talk is going to be very, very simple. It's an incredibly simple model. And so just for relaxation after the lunch. So I'll talk about a very simple two-body problem with a non-reciprocal interaction. And the interaction can be both short-ranged and long-ranged. I'll discuss the main results, and you'll see that even in this simple problem, so just a simple two-body problem. There's something interesting there, some universal behaviors, and which is the sort of main point of this talk. So I'll first tell you the results, and then we'll discuss a little bit of some heuristic arguments about how to get to these results. And I'll discuss about some exact results in some special cases, and then summarize and conclude. Okay, so the motivation for this talk actually comes from non-reciprocal systems. So non-reciprocal systems means where the Newton's third law is violated between two particles. Okay, so every action doesn't have the same equal and opposite reaction, and this is actually more of a rule rather than exception in many, many systems. For example, in predator-prey systems in ecology, then you have this bird flocks where the dynamics of the leader is different from the followers in the flock. Then the human interactions and many other systems that you can think of in swarms and school of fish. And so it's more of a rule rather than exception. And there's an explosion of activities in many condensed matter systems over the last few years on with the non-reciprocal interactions. So again, I mean, simple examples are predator-prey interaction. I mean, the predator is chasing the prey, but the prey doesn't chase the predator. So this is a non-reciprocal interaction. Then, of course, the human interaction. You may love somebody, and this somebody may not love you, and this is very common. Okay, and and this is and as I said, there's an explosion of research activities in ecology, finance, active particles, neuronal activities, social interactions, metamaterials, and many other places where the effect of non-reciprocal interactions when the Newton's third law is violated. So that has led to very interesting physics, new phases, and many interesting properties. So which I'm not going into the details of all this. But what is really lacking in this field is there are very few exact results. I mean, there's hardly any exact results. I mean, mostly simulations and other things. So we wanted to amuse ourselves with some simple model, and that is which led to this work. And I forgot to mention that this was a joint work with Purna Basu from SNBC Calcutta, and Paul Krapivsky, who is in Boston, and this is a recent publication here. All right. So this is the main motivation basically. So we wanted to find a very simple model which we can understand, and not just by simulation or something. And so with that thing, so I'll just introduce you the model. It's just this very simple two-body problem. Okay. So imagine that you have two particles. So one is a blue, which I call the driver particle, and the red, which is a driven particle. So you can think of this as a predator and a prey. Okay. So for example, the driver could be the predator and this red guy could be the prey, or opposite, or vice versa. And in this model, the driver performs very simple Brownian motion. This is in any dimension, let's say. So dx dt is square root of 2d. D is the diffusion constant, and eta of t is just a zero mean Gaussian white noise with delta correlator. So trivial, it's simple, just a Brownian motion this guy is doing. But the passive particle, that means this driven particle here, so it has a slightly different dynamics. It's completely slaved to the dynamics of the driver particle. So dy dt is just some function, which is a force, is overdamped, both are overdamped. So some function of the distance between the two particles. And for simplicity, I'm just going to assume that it's a central force. So you can write it always as a derivative of some potential, and this potential is spherically symmetric. Okay? So that's it. This is the model. Okay, so X is trivial, and Y has this F in it, force in it. So you can think of this. Now, this force can be either repulsive or attractive. So, for instance, you can think of this as a lazy predator, and if this is a prey, the prey is just doing a Brownian motion, and if it is a short-range force, this predator makes a move only when this guy is closer to it, and in that case, it's maybe the attractive interaction because this predator wants to catch the prey. So it's F is negative here. On the other hand, if you think opposite way, if you think of this guy as a lazy predator, and this is a prey which is going around doing Brownian motion, when it comes closer to it, this guy gets attracted to it. So yeah, sorry, this is the attractive, and the repulsive is when this is a prey, because the prey wants to run away from the predator, and so it's a repulsive interaction. So this is the problem. Okay, so we have X coordinate is this, Y coordinate is that. F is given to you. F can be positive or negative, attractive or repulsive. And all I want to know, so some examples of short range. By short range, I mean that f of r decays faster than a power law as r goes to infinity. For instance, you can just take a Gaussian decay here or exponential decay if you want. So, and if you write in terms of potential, so it's repulsive if the V0 is positive and attractive if V0 is negative. Yeah.
If both X and Y have
yeah.
Presumably you can go to a center of mass of X.
Yeah, I'll come to that. Yeah, depends on what question you are looking at. Of course, you can go to the center of mass, okay. But that will not tell you what is Y doing. Just give me 1 minute, okay. So first let me define the model. So, this is my F, and if F has a power law tail, so this is a long range interaction, okay, then exponent A positive. So again, here it will be repulsive if A is positive and attractive if A is negative. So that's the model. Now, what is the question I'm interested in? And here I'll reply to Gautam's comment. So the question I'm interested in, so if I look at the driver particle, so it's trivial, right? X square is just a Brownian motion. Driver is not affected by the driven particle, okay? It's just doing its dynamics on its own. So X square average goes like 2 dt, and the position distribution of the X particle is just simply trivially Gaussian, d-dimension. So the question I'm interested in, what is the mean square displacement of the Y particle? Okay? And what is the position distribution of Y particle? So you give me F, and I want to know what is the statistics of Y of t. That's the problem. Okay? This is very, very simple, right? So where is the difficulty? So as Gautam says, that you can go to the relative coordinate, x minus y, and indeed, you can solve the problem. You can get P of x minus y. Okay? And you know P of x. But you cannot, from that, you cannot derive P of y so easily. Okay? So where is the problem? What is the technical problem? So let me just tell you. So these two guys here. So I can write down a Fokker-Planck equation, P of x comma y comma t, for instance, in one dimension. So the Fokker-Planck equation is very simple. So there's a diffusion here because of the x coordinate motion, and there's an advection here due to the y coordinate motion. It's just, very, very simple equation, right? You start from some initial condition. And all you have to do is to solve for P of x, y, t. And so if you are interested in the marginal distribution of x, it's very simple. You integrate over y, this term just drops out, you get back diffusion. But if you are interested in y, then you have to first solve for the full problem, P of x, y, t, and then integrate over x to get the marginal distribution of y. And this is very hard. Okay? It's not so easy. And so why am I interested in this problem? So the statistics of y, so this is the question I'm interested in, statistics of y. So you would think, okay, if it depends on what the force is, of course, and why would I, be interested if it is, If it depends on f and it's non-universal, so then there is no interest. Okay. The amazing thing is, as we will see in a minute, that this result actually is completely universal. Okay, so let me just show you this. So I'll first discuss the result, and then I'll just tell you how we get to this result. So what is the result? So first result is that in d equal to 1, the y square of t universally goes like square root of t, irrespective of fr, as long as fr is short-ranged. Okay, so I'm talking about short-range forces first. So no matter whether you take Gaussian, you take exponential, whatever you take, y typically scales like t to the 1/4 universally. And this is, so it's a subdiffusive dynamics which is generated by this, no matter what f you take. And it's the same for attractive and repulsive. You can take attractive force, repulsive force, doesn't matter. It's always t to the 1/4. In d equal to 2, sigma square goes like log t, again universal, it doesn't depend on the f. And for d bigger than 2, of course, it's of order 1, it hardly moves. And in that case, it's non-universal. So its universality holds only for d less than equal to 2. So this is just for the mean square displacement. The average, of course, is 0. This is the second moment. Yeah, I'll come to that. So yeah, I will see why is it obvious. So, now, what about the distribution? Is that universal? Indeed, the answer is yes. So if I scale by square root of t to the power 1/4, this is a scaling function to 1 over t to the power 1/4, some scaling function of y over t to the power 1/4 with some non-universal constant thrown in here. And this function f on z is again completely universal. It doesn't depend on f. Doesn't depend on whether f is attractive, repulsive, as long as it's short-ranged. Okay? And the answer is highly non-trivial. So this is the formula in terms of hypergeometric functions. But the amazing thing is it's completely universal. Okay? So this function it goes to a constant as z goes to 0, and it has a cusp here, mod z, and it has a tail, which is super exponential, but sub-Gaussian, so it's z to the power 4/3. And again, I mean, if it was depending on completely on the f of r, I mean, why would I do this calculation? But what is really was surprising is that this was completely universal. So this numerical simulations was done with, at different times to show the collapse, and also with many different types of short-range potentials, and they all fall on the same curve. So that's result number 1. Now, let me just, mention at this point that this t to the 1/4 is a very common exponent in one dimension in many systems. So, for example, one of the systems that was mentioned here yesterday, this is a symmetric exclusion process. This is a very famous, well-known process that many of you know. So imagine that you have a lattice, and at each side you can have at most one particle. So these are hardcore particles. Okay? And each particle, with probability half, tries to jump to the right, and with probability half jumps to the left, tries to jump to the left. And it can actually go there, provided there's a vacancy. If there's another particle there, the move is rejected. Okay? So hardcore particles. So this is a very well-studied system, and if you just tag one particle, okay, this guy, and you ask, what is its mean square displacement at a long time? So it's known that this goes like t to the power half mean square displacement, which means that yt typically goes like t to the 1/4. So that's another example. And here it becomes subdiffusive. It's very easy to understand because, I mean, essentially there's a caging effect. I mean, this guy is surrounded on both sides by occupied particles. It really cannot move that much, basically. So it moves a little bit, but it gets caged by the other particles. So it becomes subdiffusive. But the scaling function, the full probability distribution function of the typical displacement y, this is a well-known also, and is well-known for a very long time in the maths literature. It's just a simply Gaussian. These days, I mean, people are studying the large deviation tails of this distribution. Tridib was involved in that, and many other people also. But most of the probability is contained in the typical distribution, near the peak, and that is typical distribution is Gaussian. So, and this is very, very simple Gaussian, some simple function. Compared to that, in our case, you see this function is highly non-trivial. It's non-Gaussian and quite non-trivial behaviors. All right, so this is the one dimension. How about two dimension? 2D, again, the result is that it goes like log t, and if you scale by square root of log t, distance, again, f2z is completely universal, but it has a rather simple form. It's just 1 over 2 pi times modified Bessel function of argument index 0. So it behaves like minus 1 over root pi log z as z goes to 0, and it decays exponentially for large z. Now, this result actually it looks much simpler compared to 1D. And in fact, I mean, this problem appeared in disguise previously in the literature. And this was actually goes back to what is called the vacancy-mediated diffusion. So this problem appears in many different areas, glassy dynamics, dynamics of defects in crystals, and so on. So imagine that you have a square lattice, and you have, particles occupying the lattice, and there's only one vacancy. Okay, so it's extremely dense limit. There are all these particles which are filling up the lattice, and there's one single vacancy here. And you tag one particular particle, let's say this guy. So this guy, most of the time it's not moving, and it moves only when the vacancy comes close to it, because then it can hop to the vacancy site, or in other words, the vacancy comes to the left. So the vacancy diffuses, and this guy, moves only when the vacancy comes back to its position. And this is sort of what is responsible for the slow logarithmic growth of the mean square displacement in this problem. So here also it is known, as I said, this was lattice model, vacancy mediated, and this was studied by many people here. And position distribution also was known, and it's exactly the same function. Okay? But this result was obtained by very complicated computation, okay, on the lattice and all these things. But I mean, the result we have is actually continuum, and it doesn't depend on whether the force is attractive or repulsive. Okay? So this is the short range interaction. Okay, so now, yeah.
What was non-reciprocal in this example of vacancy is that the vacancy moves independently.
Yeah, I mean, in this case, I mean, basically, this is not directly our model. It's a different model. Okay, it's a different model, but you see the same log t growth and same scaling function that appears. Okay. We'll see later that there's some similarities between the mechanism, but it's not really non-reciprocal model that I was talking about. Our model was very clear: if these things, and you get this same result. But I was saying that this t to the power 1/4 growth or the log t growth appeared in many other interacting particle problem in before, okay? But here it appears in non-reciprocal problems, okay? But there's no direct these things that they are similar. Yeah.
For the 1D case, when you found exponents like single file diffusion.
Yes.
For the 1D case.
Right.
For the 1D case, when you found a single file diffusion exponent, there we know that it is some kind of an gauging effect. But
for the shape.
For the shape problem.
Yeah. For here, I've not explained to you. I'm just telling you the results. I will come to the explanation. Okay. Long range interaction. Gautam was asking. So what's our result for long range interaction? So it's actually y squared t here now. For the driven particle, it depends on. So here are the results. So if this exponent a is bigger than 3/2, okay, so then it's like the long range, short range interaction. It goes like t to the power 1/4, and the scaling function is again universal. Same exactly what I showed you before. If a equal to 3/2, it goes like square root of t times log squared t. And if a is between 1 and 3/2, it's an exponent which depends continuously on a. So it's 2 minus a. So here it's all universal again. But when a is between 0 and 1, which is basically ultra long range interaction, if you like, so there it depends on the sign. For the repulsive case, it goes like this exponent here, and the attractive case, it goes diffusively. So there is a phase transition at a equal to 3/2 from the short ranged to long ranged, basically. So in other words, if you see this MSD, if you say the mean square displacement goes like t to the power some exponent phi, then this phi as a function of a is quite interesting. So for a bigger than 3/2, it goes to the short-ranged value, which is 1/4, I mean, y squared, so it's half. between these, it is a straight line, it's 2 minus a. And then when a is less than 1, then it depends on whether it's repulsive or attractive. In repulsive case, it goes like this. And attractive case, it becomes ballistic at a equal to 0, when a goes to 0. And for the attractive case, it remains diffusive all through. So there is a quite a rich phenomenology even in this very, very simple problem, okay? And I want to now tell you how we arrive at these results. And so that's the sort of next part of the talk. So first I'll give you some heuristic arguments, what is the reason for this t to the power 1 quarter? And you will see that this is very different from, there's nothing to do with this shape, because shape is an interacting particle, many particle system. This is just a two-body problem, okay? So let's think of, for simplicity, just one dimension, and imagine that this f is short-ranged, and let's say it's repulsive, and you'll see the same reasoning works for attractive case also. So you are this driven particle here, you are the, whatever prey or predator, completely slaved by the other guy. So other guy is just doing Brownian motion. So imagine that this guy is coming from the left, and you have repulsive interaction. So when it's far away, this red particle doesn't feel it, but when it comes closer, because it's short range interaction, when it comes closer, this guy, because of repulsion, it moves to the right, let's say, goes away a little bit. On the other hand, if this guy was coming from the right, then it moves to the left a little bit, right? Only when it comes closer to it. And so it sort of undergoes a displacement, which is plus minus 1, whenever the other particle comes close to it. And you see that for the attractive case, it will be exactly, if it comes from the left, then the attractive case, this guy will move to the left, whereas if it comes from the right, it will move to the right. So delta y will be still plus minus 1. No, it's not a lattice model, but I'm saying that, just imagine that this is a heuristic argument. I mean, basically, you just say that, okay, it comes, it's short range interaction, so it just moves a little bit, okay? So it's not a rigorous argument, okay? So therefore, y of t, the position of the typical position of the driven particle. So this is just a, sum of these plus minus 1 terms up to where the sum goes from 1 to nt, because nt is the typical number of returns of the random walker to this position. See, this guy is not moving that much. So you can think of random walker comes, it comes back. Every time it comes back, this guy either moves to the right or to the left, okay? So essentially, it's this sum over plus minus 1 up to n of t, where n of t is the typical number of returns in time t of the driver random walker. And so by central limit theorem, you see that, y of t will scale typically like square root of n of t, both in the attractive and repulsive case. And it's well known, and it's very easy to prove, that in d equal to 1, typical number of returns of a random walker to the origin goes like square root of t in time t. So, and that gives you the t to the 1 quarter. And similarly, in d equal to 2, typical number of returns to the origin goes like log t, and therefore yt goes like square root of log t. So, and the main assumption here is a short range interaction. So this y guy is not moving that much. It moves only when it comes back to these things, right? So, and so you have to do a little bit more work to derive even the position distribution by the same argument. So to derive the position distribution, so basically you condition on n being the number of returns in time t. So if I condition on that, then this is just a Brownian diffusion, this y particle. N is acting like a time, if you like, number of returns. And then I have to multiply by the probability of the number of returns in time t. And then sum over all possible n. That's it. Now, again, position of the y particle conditioned on the number of returns is like the time, basically, if you like. So therefore, this will be just a simple Gaussian again, just a Brownian motion result. Okay. But then n, p of nt, probability of number of returns, so this you need to compute. But this is again sort of very easy to compute and is known in the literature. So basically what you have to do is like a renewal argument. So you say successive returns of the random walker to the origin, they are independent. So you have to do a little bit of work. They are statistically independent. So it's a renewal argument. And from this, I'll not go into the details. You can very easily derive that P of nt also has a Gaussian distribution e to the power minus n square of 4t divided by 1 over square root of pi t. Okay? And in 2D, this is n over log t by log t. So you just plug in this expression, these two things. So there's a condition on n, it's a Gaussian distribution, and the n itself also has another Gaussian distribution with t as a variance. And you replace this sum by an integral, and you arrive at this result. This is in the large T limit. And this you can do easily. This actually you can do exactly this integral, and this is what gives you. So this scaling function is precisely this, and if you do this integral, you get this orbital function. Okay. But this is completely universal again. It doesn't depend on the detailed nature of f. Yeah. So short range basically, see, the point is this conditioning, because I mean I'm saying that it's y guy, it hardly moves, right? It's just static, because if it's a short range, that means it feels the presence of the other particle only when this particle is very close by. Otherwise, it doesn't feel. It's not moving. See, dy dt is f, right? So f is, I mean, is there, but you know, it hardly moves basically. I mean, because f is very far. F falls off very quickly for short range forces. So f is basically 0, so it's not moving. It's staying there. And this guy makes one trip, comes back. Only when it comes very close to it, it fills, and then it moves a little bit randomly, either left to the right. And then again, it makes an excursion, and then it comes back. And so every time it makes an excursion, it drives this particle randomly to the left or right, basically. So that's the argument. So basically, and then you divide the thing into 2 bits, you condition on the number of returns, and then you know if you have n number of returns, this guy would move e to the power minus y square over 4n. And then a distribution of n you have to calculate separately. And then you just put them 2 together, and then that's it.
The amplitude of the force also never comes in.
No, it doesn't come. And you'll see some exact results after that, okay? You'll see this. Yeah.
Some diffusion to the y, independently.
No. If you add diffusion, everything will go away, because then it'll be just, it will dominate everything. Okay? So, no, so this is a totally non-reciprocal interaction. All right, so same thing, you can do it in 2D. And 2D, if you do, you know, it's just this guy times this, and if you do this integral, you get k0 of z that I mentioned. This actually, in the end, is very simple derivation, these heuristic arguments. And so what I want to show you is now, just to show you some exact results in some special cases where you can actually solve it more precisely. So let's see one example. So I mean, I will just, you know, focus myself in d equal to 1. Okay? So I have this, and fz is therefore in an odd function. You know, if it is positive, it's attractive. If it is negative, it's repulsive, or vice versa. So imagine that they start both from the origin. And so now what I anticipate and prove a posteriori is that the y undergoes a subdiffusive motion. That means the modulus of xt is always much, much bigger than y of t as t goes to infinity at late times. Okay? So then you see that this y guy here, so if I ignore the y of t compared to x of t, okay, then I can integrate, and this just becomes a Brownian functionals. Right? So x of tau is a Brownian motion, and you are interested in the properties of a Brownian functional, where the force is the functional here. So Brownian functionals have been, you know, studied quite a lot in the literature, and you can actually do many things. So let's see. So suppose I want to calculate the y square, mean square displacement of this guy. So this will be, you know, if you just compute this, it just requires this 2-point correlation function of ff. And so ff correlation function is just fx to fx1, and then you have these propagators here. Propagators are just Gaussian propagators. It's very simple. So you plug in, and you just work in the Fourier space, Fourier Laplace space. And what you find is that the mean square displacement, if you take the Laplace transform with respect to time as a function of s, this is an exact expression which is given by this. So these are the Fourier integrals. And f hat of k is just the Fourier transform of fr. And the late time behavior is governed by the s going to 0 limit. So you just have to, you know, analyze this integral in the small s limit. I'll not go into the details. And what you find is that all the information about f is actually, so all, you know, in the small s limit, essentially the small k behavior matters in this integral. And you see the small k goes like some you know, I A1 times K A1. So F is, information about F is encoded in A1, but this is just overall amplitude. In the end, you could just to look at this small s behavior, it goes like some non-universal constant times 1 over s to the power 3 by 2, which means that y square, which is the, if you invert this Laplace transform, it goes like square root of t. And okay, I mean, there's some non-universal scale factor here, but this is completely universal. And similarly, you can calculate the position distribution, now full distribution, not just the mean square displacement. So to compute that, it's best to look at the Laplace transform of the position distribution with respect to position now. So if I call it Py, then this is e to the power minus p into integral of that guy. And this is I call Qp starting at x0 of t. So x0 is the starting point, and you want to know what is the statistical properties of this functional. So you just look at this cumulant generating function or Laplace transform if you want. And once you have that, you have to invert the Laplace transform to get the position distribution. Now the Qp of xt, of course, those of you who are familiar with Feynman-Katz, that this just satisfies the Feynman-Katz equation. This is my fake quantum mechanics, because if you go to imaginary time, this is just a time-dependent Schrodinger equation. So it's very easy to show that this functional here, Qp of x naught t, it satisfies this Feynman-Katz equation. So I have to just basically solve this equation for a given f and find out the the Qp of x naught t, and then invert the Laplace transform with respect to p to calculate the position distribution p of y t. Okay, so therefore, f of x naught here, your force, that behaves like a quantum potential in this language, in this Schrodinger problem in imaginary time. And of course, time-dependent Schrodinger equation, you cannot solve it for general potential, quantum potential, we all know that. So, but there are some special cases for which you can solve, and that's what I'm going to show you. So I want to focus on some, short-range force, which means the corresponding potential will also be short-ranged. The first example, you just take a square potential like this, rectangular potential, if you like. So Vx is V0 here, between minus R to plus R, and 0 outside. So the force, therefore, which is the derivative of the potential, is just these two delta. It's an odd function. So it's two delta peaks here. Again, V naught positive means attractive, and V naught negative means repulsive, or something like that. I mean, opposite way probably. So I have to just solve this, Laplace transform. So I take a Laplace transform of this my Qp of x0 t. I'll not go into the details of the computation, but you can calculate for this case, and it's just elementary quantum mechanics. You just solve this, and you find this is the answer. R here is this range here of this potential, and P is the Laplace parameter, and S is the Laplace transform with respect to S, and so on. Okay. So this is exact. And then from there, you can, you can extract from this Laplace transform by taking the double scaling limit. S goes to 0, P goes to 0, keeping the ratio P square over S fixed. And you arrive at this, this exact result of y square. So here you see the amplitude is non-universal, is 4R V naught square, but this exponent is universal. Okay, so smallest limit is just this, and from that, you invert this Laplace transform exactly, and you get back precisely what I told you about from the heuristic argument. So it comes out from the exact Feynman-Katz equation for this particular example. You can work out, play around with other potentials. For example, you can take a triangular potential like this. Okay? So Vx is V0 into 1 minus mod x by R. So here the force is, it is plus V naught over R if x is positive, and if x is positive and less than R, and minus V naught of R if it's within the range. So it's a short range thing. So again, in this case, you can do exactly same calculation for the Feynman-Katz, and you can solve the time-dependent Schrodinger equation exactly. I need the time-dependent Schrodinger equation. That's the only technical difficulty. And, lo and behold, here the C1, of course, is non-universal. It depends on the explicit form of the potential. But once you scale it by t to the 1/4, you get back exactly same universal scaling function. Okay? So it really doesn't depend on the nature of the short-range force. Okay, so here there's some numerical check for different types of potentials and different these things. You always recover the same exact universal scaling function. So let me just summarize so far. I mean, so what did I say? So, this is the D equal to 1 driven particle. Okay? Position distribution is universal as long as the force is short-ranged. And, it really is completely universal and doesn't depend on the sign. It doesn't depend on this attractive or repulsive interaction. And same thing for D equal to 2, except that the scaling function, of course, is different. Now, what about the long-range interactions? And here are the sort of open problems. Long-range interaction, we have very little results, and there are many open problems. So that's what I wanted to tell you next. So for the long-range interaction, again, this result that I mentioned before, Laplace transform of the mean square displacement, this is, of course, exact for any f. Long or short doesn't matter. And from this, if you take, for example, long-range force, a over x to the power a, so that means the Fourier transform for small k will behave like this. So you plug in there and you do some analysis here, small x. So what you find is that the y squared t, after inverting the Laplace and Fourier transform, that it goes like t to the power phi, where this phi is max of 2 minus a and half. And of course, this result is valid as long as a is bigger than 1. Why did I assume that a is bigger than 1? Because, I mean, you want the driven particle to be subdiffusive, because remember, to get to the Brownian functional, I had neglected the y of t in the expression of f of x minus y. So that means I'm assuming that y is slower than x, and that is true only if a is bigger than 1. So for any a bigger than 1, this is the exact answer for the mean square displacement. So this means that there is indeed a phase transition at a equal to 3 by 2. So a less than 3 by 2, I mean, a bigger than 3 by 2, you go back to, again, the universal short-range result. And for a between 1 and 3 by 2, you have a t to the power 2 minus a. So the exponent depends continuously on this a. It's a subdiffusive. And there is a transition exactly at 3 by 2. In fact, if you look at the position distribution across this critical value 3 by 2, so you see that so this is for a equal to 1.2 and this is for a equal to 1.9. So a equal to 1.9, you have a beautiful, universal distribution that I, gave you an analytical expression for. For a equal to 1.2, this guy has a double peak structure. And this, we don't have any analytical result for. So that's a completely open problem. It's universal again, okay. But still we could not compute it exactly, this function. And so that's, I find this quite amusing that this is universal and yet we cannot compute, and it would be nice to compute this, this case for any a between 1 and 3 by 2. And now on the other hand, in the ultra long range case, when a is between 0 and 1, then you have very different behavior depending on the attractive or the repulsive case. So if you look at the repulsive case, so what happens is that, the repulsive case, very, very big force, basically. It's ultra long range force, okay? So this, it decays very, very slowly. So because of this huge force, basically the driven particle becomes super diffusive, okay? So effectively, what happens is that in the dy dt, you can just, replace the, I mean, x is not moving much, and essentially, f of x minus y is just f of y, which is 1 over y to the power a, and when you integrate, it's like almost deterministically, it moves away with an exponent t to the power 1 over a plus 1. In the attractive case, on the other hand, what happens is that the driven particle gets totally slaved to the driver particle, and they move like a dimer. They bound pair, essentially. The overall, it goes diffusively, y square of t. And so this is the result for the a between 0 and 1, that you have a repulsive case, it goes like this, and attractive case, it goes like this. And this has been checked numerically also. To summarize, I mean, for the long range case in d equal to 1, what we have is that for a bigger than 3 by 2, again, it goes like subdiffusively as t to the half. A between 1 and 3 by 2, it goes like t to the power 2 minus a, with a transition here, and exactly at the critical point, it goes like root t log squared t. And when a is ultra long range, that means, if it is between 0 and 1, then it depends on the repulsive and attractive. I mean, repulsive case is this, and attractive case is that. But the point is that, as I said, apart from these two, I mean, all these three cases here for a less than 3/2 or even a equal to 3/2, we cannot derive the full distribution of y of t, in particular in this range where it's completely universal. Okay, so that's a completely open problem. And okay, so this is the sort of result for the exponent for the repulsive case. So let me just summarize and conclude. So essentially what I talked about is a very, very simple toy model of two-body problem with non-reciprocal interaction, where the driver particle is doing Brownian motion and the driven particle, which is completely slaved to the driver, either by a short range or long range central force. Okay? And I mean, for me personally, what was interesting here is the fact that it's completely universal distributions in the d equal to 1 and 2, which we did not expect right from the beginning. And so that's the sort of main punchline. And we could derive the exact scaling functions, of course, for both d equal to 1 and 2. In some cases, I mean, mostly, I mean, first by heuristic, and then, in some cases, we can solve it exactly. I mean, wherever you can solve any time-dependent Schrodinger equation with a sort of local potential, essentially, you can check that this is a universal result. And so there are many open questions. I mean, as I said, exact scaling function for the long-range force, it's universal, and we still do not know what the distribution of the scaling, what the scaling function is. Then you can actually imagine that you have many driver and many driven particles. So one you can go to Mn, and here maybe you can do some hydrodynamic theory or something like that, as many experts here. And so that would be interesting to look at. And the last thing that I want to tell you, it's nothing to do with the talk. This is a little publicity about Journal of Physics A. So I became the chief editor since the beginning of this year, and actually the journal asked me to publish as this journal. Okay, I was asked, and this is the fault goes to Jerome, because he's the guy who who actually suggested to the board that I should publish as this journal. So I'm doing it. So this is of course senior people, you all know about this journal, but for the juniors, I mean, this is a very good journal, very solid journal in statistical and mathematical physics, and it's not a flashy journal like Nature, Science, etc., where you have to pay enormous amount of money. Here you don't have to pay anything to publish your paper. And you get referees who actually read your papers and make some constructive remarks or something or the other. So for the younger people, please do consider submitting your papers to JFISA if you have not done it already. And okay, so with that I'll stop my talk. Thank you very much for that.
Yes.
So these many drivers in one driven, that seems fairly straightforward. Like n of t is the sum of different particles arriving, so it will be just additive.
Yeah, no, absolutely. But what happens there? Okay, we have not done the competition, but this driver part, the driven particles. So if, let's say you have one driver and you have many driven particles. Okay.
That is different.
Yeah, then it's very interesting, because then these driven particles, even though they are non-interacting, they get strongly correlated, because they get, by one driver which correlates them, every time it comes back. And there's a very non-trivial correlations which get generated between these driven particles. Okay, so this goes into a sort of, I mean, it's still time dependent, of course, but
it will not go into the statistics of R squared of one single particle.
Yeah,
okay.
Exactly.
Any other questions?
There's a trivial special case in which the driver just sticks to the driven. So one way, it will just inherit the motion of the thing, but the other way not. So half of the time, it will behave like a
diffusive particle, right.
But the other half,
other half not. But overall, then it will be diffusive actually, because they're going like square root of t. Yeah, and so other guy is probably the order 1 difference. So overall, if you calculate the y squared, it will still go as diffusive in that case. So. Sorry, can you, I can't hear you, yeah.
Teamwork. So the heuristic argument that you gave and for the short range case, it also, same argument appears into the last talk in the anomalous fluctuation of the current, and the same scaling function appears,
I see.
and the same argument appears there.
Okay.
So I just wanted to make this remark.
So it's a very easy, very simple argument, basically. So.
Your distribution might remind something like the stable distribution that comes from center.
No. Stable distribution means Levy
Yeah,
stable
it doesn't
distribution.
look like, but it's, of course, if it looks like the universality shows that there is a really some universal distribution for whatever the F you take, right?
Yeah.
So I was just asking the question, is there any analog of those kind of stable laws?
No, it has nothing to do with stable laws always have a power law distributions. Okay. But here you have a e to the power minus z to the power 4/3. It's a stretched exponential tail. So it has nothing to do with the stable law actually. Stable law means, if you take a sum of n random variables which are independent, and each of them, let's say, has a power law distribution, then the sum will also have the exactly same power law distribution once properly centered and rescaled. Okay. And that distribution is always a power law. This is what the Levy distribution is. Okay. So it means the Fourier transform of the position distribution will be e to the power minus mod k to the power alpha, where alpha is between 0 and 2. But that has nothing to do with this.
Questions? Okay, I would like to ask one.
Sure.
How important is it that the central particle, the driver, that shows this Brownian motion, if it has some other type of
No. You see,
motion?
this is a very, this was just a toy model just to see what, what kind of universal behaviors you can. You can, of course, embellish many other things. You can add noise, you can add this, you can add
I'm
this, you
asking
can
that,
explore.
will this
No.
remain valid?
No. I mean, that depends on what is your model. So it's when you have to work. So that's what I'm saying. This is a very starting problem. So we can, consider many modifications of it and, explore the things, universalities and other things, classes and things like that. So.
Questions? Let's thank Satya for a wonderful